I'm Dr. Miller. I'm going to share with you how I think we can teach math in a better way by illustrating this with how I learned to plot polynomials. Our education system has developed all the techniques needed for teaching to a great curriculum in mathematics. It just doesn't know how to implement it. This was well illustrated in the colossal failure of the Common Core curriculum and the attempts to rescue it. The key parts in the implementation are the teaching and application of the fundamentals needed to promote the understanding of mathematics and the teaching beyond the current edge of knowledge. To illustrate the thought processes needed to use that learning to solve problems beyond what we were taught to solve. This builds our confidence to encourage us to spend the time and effort to do so. The reward is the satisfaction of accomplishment. My goal is to try to surpass, in some areas of math, those mathematicians on YouTube who increased my knowledge beyond what I was taught. Among these presenters are 3 Blue, 1 Brown, Mathologer, and James Tanton. In return, I want to teach my students so they can learn beyond what I was taught. I often point out to them that they are far smarter than I was when I was their age. My professional skill made me the leader in computer graphics. Since that time, many people have surpassed me in my skill, though recently my work was referenced in a business magazine, including the Harvard Business Review, about my work in relationship to the TV series Mad Men. However, I found that my shortcomings in my education that required me to teach myself topics that I thought should have been taught to me. Today, I would like to share with you my experience so as to help to plant the seeds for reshaping how math is taught. We first begin with an outline. This is how we organize our thoughts and provide direction and aim. Mathematics is taught to the edge of understanding. We teach by rote. We teach a limited set of tools, applying them to limited examples. We do not complete the teaching to understanding. We do not develop the skill to develop confidence. We do not show the easiest way to solve a problem. We do not effectively teach organization. We do not effectively teach how to practice. We do not lay the best of the seeds for creativity. Good students end up teaching themselves using the limited knowledge that has been presented by their teachers. I'm going to illustrate this by teaching one how to plot a graph of a function. I choose the cubic function y equals x cubed minus 3/4 x minus 1/8. Normally, we're taught to factor that into components by figuring out what the numerical values of those factors should be. But it turns out this one is minus sine of 10 degrees, minus sine of 50 degrees, and the sine of 70 degrees. There's no way that we could intuitively factor those out. To illustrate that these are the correct answer, I choose this minus sine of 90 degrees, plug it into 4 values, do the calculation, and get approximately 0. However, we are taught the Newton-Raphson technique, which allows us to use the reiterative formula, which is x equals x minus the function divided by the derivative of the function. The trick is, of course, picking a good starting seed. In this case, I pick minus 0.1, and after a few iterations, I get the answer good to 4 decimal places. With another few iterations, I can get it well beyond 8 decimal places. We could also then find the maximum minimum by solving the derivative for its roots and get minus 0.5 and 0.5 as the x values. We then plot those 5 points that we calculated, but in order to get a better feel for the curve, we put a few more points in between. And somehow we're hoping that the more points we put on there, the more they will follow this mathematical function. Okay, well, it turns out that the way we discover how points are related or correlated is by taking the slope using adjacent points and seeing how close they come to each other. If they're very close, then we feel that the points are part of the same curve. In the slope, it is the slope that is allowing us to make the assumption where we know points lie next to each other. when the slopes are approximately the same, that is the key concept. Okay, so now I'm going into a cubic function, which is cubic both in the independent and dependent variables. And what do I get on my right? A circle and a line, two curves. What's going on here? We have been taught how to plot this. It would be tedious and near impossible to manually generate the plot. However, we could factor this with functions rather than numbers. Assume one of those functions is a line. We take an arbitrary line, and in dividing that into that equation, we determine what the slope and y-intercept are, and we get a circle as the other function. This concept will work with any line and conic section, whether it be a circle, ellipse, a parabola, or hyperbola. Whole new area that I was unaware of. Now we can plot each function separately using the quadratic formula. Key to this discussion was that we could use the distributive property to factor our polynomials. Now, normally what we do is we get a set of data. And on the left, we have points that will end up being a straight line, the middle a parabola, and then on the far right, we have the elliptic cross sections of a cone. And what we notice is that we can find a function that will allow us to calculate those points, given points. However, the beauty of the function, it allows us to go beyond and also to interpolate in between. And so we're assuming that those are parts of the curve, we interpolate what we think the rest of the curve will be. But what holds them together? The continuity, the slope of the lines. Okay, and so what we see here is we've drawn a line through a set of points. This was a parabola, but we would need more points to really be sure that it was a parabola. Over here, we've taken a three-dimensional plot and shown that to plot that in 2 dimensions, we go to a concept called contour plots. We never do contour plots in school because it's too computationally intensive. Over here, we've shown plots could look like this. We don't see any correlation between the points, but as soon as the points start getting close together, we begin to see a correlation, and the closer they get, the better the correlation. So now I'm going to look at a contour plot, okay? And this is a contour plot of a parabola, okay? And what we're actually seeing of the parabola is the plane that goes through this contour. Let me show you what that looks like in 3 dimensions. So I've taken a 3D computer to plot this. And if you look at it, these are the red points that we see on the ends of that line. And if you look closely, you can see parabolic sections as we go through the complex plane. Now, the reason why I use that is because now we can understand this better. The red is the high points and the blue are the low points. So we can see the parabola as it goes down and then comes back up again. And this is in the complex plane, where this is the complex portion, this is the real portion. So we picked when the complex portion was 0, and that was the slice of the 3-dimensional plot that gave us our parabola. You also notice I use a plotting of the Newton-Raphson approach as we got close to those roots. And it turns out we see in one case where we just keep going off the graph. So we have to be careful about how we choose those roots. Okay, so now we look at the simplest of curves, a straight line. And what really defines a line? That's slope. Every point with its adjacent points will have the same slope. Okay, and then we can write this in equation. Y is equal to mx plus b, where m is the slope, the change in the y value with respect to the change in the x value. And we also talk about those are lines that have the same slope. And then perpendicular lines, lines which have the negative reciprocal. And it turns out that those concepts were what I use to develop a patent for map graphs on a computer. And the next thing we have is transformations. We do get this in school, but there's a little bit of a hitch there. First, we have the translation, which is relatively straightforward. You can either move in the X or Y direction or both. But then we have magnification or dilation. And what happens here is we have a point of magnification. We don't think about that. We end up noticing that when we magnify curves, that they start moving. And so as a result of that, I found that the point of magnification, and it's helped complete what I was taught. We also have a point of rotation when we rotate, except when we get the formula, we're always assuming we rotate about the origin. Okay? And this created several conflicts, not being aware of the limitations of what I taught. I also show reflection, which is sort of somewhat ill-defined. It's a perpendicular distance from a point to a line. We extend that perpendicular and measure equal distance off at the end. And you'll notice these two cannot be obtained by rotation. Okay, so now we have some fundamental building blocks with my illustrating some of the weaknesses that either we're not taught or we don't listen. Now, we need a little bit of differential calculus, and not to do a whole course in differential calculus, I show how to derive a function raised to a power. And now let's look in more detail at the Newton-Raphson technique and a parabola. And what we'd like to do is find the crossings of that parabola with the y equals 0. And what we basically do, we use the Newton-Raphson technique to calculate slopes and recalculate slopes until we converge to the point. Okay, and what I've shown in here is if we pick a seed of 1, we can find the square root of 2. However, in order to find the square root of minus the square root of 2, we'd have to pick a seed of 1. And it turns out that if there were no crossings, we get a complex number. And I discovered that the Newton-Raphson technique works with complex numbers too. Okay, now to go a little bit into an important subject, complex numbers. And basically they can be described by an amplitude, which is a radius, and an angle with respect to the x-axis. This is the x-axis and the imaginary axis. And when we multiply complex numbers, we in a sense we are doing a rotation during that multiplication. Here I show a rotation where we have our original reference plane, reference axis, and then our rotated axis, and what that point looks like from the original axis plotted into the rotated axis. And now I'm going to actually use that in taking this formula for a parabola and rotating it around the origin. And when we do that, we get a parabola with squares in both the y and the x. Now, in school, we do get a technique for rotating the parabolas, but we don't actually ever plot them because it's too hard to plot them. So a trick we could use is we could cut this parabola out, which we could cut, rotate it whatever degrees we want, and then just trace around the outline. Or we could use a computer. Okay, now I'm looking at high order functions, and this one is still with the quadratic, except we notice the square roots are starting to appear in here. Well, how did that come about? Well, this is a hyperbola, and you will notice with the hyperbola that I have lines in which the thing approaches, and those lines are not vertical or horizontal. And there is a trick that I have for being able to calculate those slopes. But then what I did is I took this and found a separate curve to define that, and a separate curve to define that, and then translated each of these curves in this direction, resulting in a parabolic curve. And what was key in that was I was using a fractional exponent. So this was, again, taking it beyond what I was taught. But I had to work a long time and hard to figure some of these things out. Okay, now I did the same thing with an ellipse, in which I took and plotted as two separate functions, translated this one this way, and this is what I got. But here what's surprising is the curve stops in the middle of nowhere. No, it doesn't stop. It goes into the complex axis. So again, complex numbers play an important role of explaining some of the things we see or don't see. Okay, now that we've gone through our second order functions, let's go into a cubic. Well, in a linear form, the cubic takes on three forms. One where there are three separate roots, one where two of the roots are the same, and one where all three roots are the same. We start creating cubic polynomials by creating them with a line and parabola, ellipse, or hyperbola. We can make the expressions more complex by rotating and translating these parts. To reverse the generating process, we might use a computer to plot the function so that we have clues on how to unravel them. Okay, so let's take a look at what we have. Here's an ellipse with a line, a parabola with a line, and a hyperbola line. And multiplying these two functions together and set them equal to 0, we now have a function that will generate these curves. Okay, now, let's look at the asymptotic lines again here. I took this function and I made two lines be the same, two of the asymptotes of the three that we could have to be the same. And this generated an interesting hyperbolic looking function in cubic polynomial. I then took it so that none of the lines were the same. And what I found was I got three cubic looking things. And of course, I could have taken a situation where I had parallel lines. Haven't looked at that, but that gives you something to go beyond with what I've shown you already. And then I got this surprise. Under certain conditions, instead of just getting three curves, I could get four curves. Okay, and so now I have a little bit more research to do in this. Okay, and then I took these and I could write them as functions. So this function represents this part, and this function represents these two bottom parts. Over here, this represents the dark black, and this curve down here. This one represents the blue, and this part of the curve down here. And some other work I did, which I've misplaced, I could actually have three separate functions for these curves. We look at some other things other than the product of functions, some that are what I call nonfactoratorial curves. In this case, we have a bell-shaped curve, which is the red one, and a ribbon-shaped curve, which is the green one. I play around with these a little bit more, and I can get now an ellipse type of function with the bell curve, and I can also form a cusp. So you can see how far I've gone and how much more I can go, but I now have the tools that I can exercise that. And what I found most interesting is I took and generated a 10th order polynomial by multiplying the equations of five circles together, which gave me this. I also tried another one with my own program. And what I get is I'm plotting this, I'm taking a Y line or plane and moving it down, and I get the intersections with these. And that's what led me to understand how do I correlate this set of points rather than have something going back and forth or all over the place. So this is where the real understanding of what plotting curves was all about and the meaning, the importance of the slope. It took me several years to study this problem and to build upon the knowledge that my teachers taught me, and for me to go beyond what I was taught and understood. Though I did not focus on complex numbers, they were key in my understanding of the plotting of graphs. I've also done extensive research in them well beyond what I was taught. I had learned to program before the topic was introduced in my education. It was important to use the computer in a synergistic fashion rather than let it do the thinking for me. I used Desmos and Math is Fun to plot my graphs. I found errors in these programs because I also wrote my own. The errors occurred in the way they handled complex numbers. The factoring of the polynomials was the biggest discovery for me, along with handling fractional roots. And now I hand the podium over to you for you to start doing your own work. Thank you.